Let's now take a look at this next problem. We have two different boxes, or two different sets of 10 boxes. For the first method of measurement, the compression is found to be 807 pounds with a standard deviation of 27 pounds. For 10 other boxes, the compression strength is found to be 757 pounds with a standard deviation of 41. And the claim is that the difference was found to be small compared with normal variation in compression strength between identical boxes. Let's use a 0.01 level of significance. So let's kind of go through our checklist. This involves a hypothesis test. This involves an average. We're looking at the average compression strengths of the boxes. This is obviously a two-sample problem, looking at two different ways of measuring the compression strength. It is also a two-sided problem, or let me say two-tailed problem. It's two-tailed because we don't have a priori knowledge about which technique would give the higher measurement. So this one's a two-tailed problem, so that would mean that our alternative hypothesis would have a not equals in it. This is a small sample. Each sample has 10 boxes. It is unpaired. It's not like I'm looking at the same 10 boxes each time. These are just two different sets of 10 boxes, so the sample sizes happen to be the same size, but it's unpaired. And finally, the test statistic that we'll need will be t, because it is a average test involving a small sample. So our null hypothesis will be that the difference in the means is equal to 0, whereas the alternative hypothesis will be that the difference in the means is something else besides 0. Okay, so now we need our test statistic. To get the test statistic, we need a few things first. We'll need to get the standard error. And the standard error is equal to the square root of the first standard deviation squared divided by 10 plus the second standard deviation squared divided by 10, its sample size. So first standard deviation squared divided by first sample size plus second standard deviation squared divided by second sample size. And this works out to be 15.5241. Next, we need the number of degrees of freedom, and this is the fairly complicated formula. So the top is going to look like the standard error, 27 squared over 10 plus 41 squared over 10, whole thing squared. And on the bottom, it'll be 1 over 10 minus 1 times 27 squared over 10, whole thing squared, plus 1 over 9 times 41 squared over 10, whole thing squared. Okay, so now it's just a matter of plugging into a calculator and hoping we don't make a mistake plugging in. As discussed in class, the largest that this can be is going to be 9 plus 9. These two numbers added together, so 18 is going to be the largest the sum could possibly be. And the smallest it can be is going to be the smaller of these two, so the answer's got to be somewhere between 9 and 18 someplace. And it turns out the answer is 15.570. Now this is a degree of freedom problem, so I will round that down to 15. So 15 degrees of freedom for this problem. Our value of t will be equal to the observed difference in the averages, 807, minus the second average of 757, that's the observed difference, minus the expected difference. In this case, the expected difference is 0 from the null hypothesis, divided by the standard error for the difference, which is 15.5241. And that works out to be 3.22078. So that is our test statistic. Clear off a little bit of space on top here so we have some more room. The next thing we need to figure out is the p-value and the critical value. So first off, let's get the critical value. So in this case, the picture is we have the t distribution with 15 degrees of freedom. And the question asks for 0.01 level of significance. This is a two-tailed test. So that means that the total area that's shaded is 0.01, which means that the area in the right tail is 0.005, half of 0.01. So we can either use the inv button on a calculator, we can use the t.inv button on, or t.inv command on Microsoft Excel, or else just simply use the table where the area to the right is 0.005 with 15 degrees of freedom. And we get that the test statistic for this problem is 2.9467. Now the value of t that appears, 3.22, is over here someplace, and so our decision would be to reject the null hypothesis. The second thing that we can do is find the p-value. So that would mean here's 3.22078. Then we find the area to the right and also the other area on the left that matches it. Now that we can do on the calculator on TI-83 even. So let me show you how to do that. So second distribution, TCDF, 3.22078 to 10 to the 99. So find the area between 3.22078 and 10 to the 99. And I need 15 degrees of freedom. So this function kind of works like the normal CDF function on a TI calculator. And then that's going to be one tail. To get both tails, I need to multiply by 2. And so I get the p-value to be 0.005715. Okay, so this number is less than alpha. So our decision will be to reject the null hypothesis. So concluding, so let me type this out. We reject the null hypothesis. In words, there appears to be a large difference between the measured compression strengths. Either because the test statistic falls over here, or else the p-value falls over there. Okay, let me show you how to do this on a calculator. So the command over here, it goes stat tests, and in this case it's going to be a test, and it's going to be a two-sample test involving the t distribution. So two-samp t test. And so we choose stats over here because I'm going to input the summary statistics. The first average is 807. The first standard deviation is 27 with a sample size of 10. The second average is 757 with a standard deviation of 41 and a sample size of 10. The form of the alternative hypothesis is not equals, and it is not pooled, which is almost always going to be the case for our problems. And so when I hit calculate, we get the numbers that we had before. The t value is 3.22078. The p value is 0.00549. Just a little bit of round off error here. The degrees of freedom is 15 as before, and we get all the other things. So this can be done with the command on the calculator as well as the method that we showed in the video here.